Hello everyone, welcome to the lecture number 5 of the week 6. In this lecture, we will explore Rawls theorem. In the previous lectures, we have seen about the Darboux theorem, where we had a two statement of the Darboux theorem, in which we have seen that f dash of c is equal to 0 and f dash of c equal to r are equivalent if you are taking r equal to 0, right? So here in the Rawls theorem, the extended version of that one is the Rawls theorem, and it is quite applicable in solving the problems. So we will explore examples and Rawls theorem. So sometime, as you can see, that if a continuous function and curve of the continuous function cut at 2 points horizontally, then that means there must be some curve, some hump, and that hump either concave or either convex, that hump leads to the Darboux theorem. That will be the idea, intuition. The Rawls theorem has been evolved. So Rawls theorem is an important basic result about differentiable function. Like many basic results in the calculus, it seems very obvious. It just says that between any 2 points where the graph of the differential function fx cuts the horizontal line. You can see here this is the horizontal line and it cut here, right, at the same point, then there must be a point where f dash of x equal to 0. So between these 2 points there must be some point where f dash of x equal to 0. Remember this one, the point is not a unique point. Simple example, as you can see here, let's say here we have cutting like this one. So a and b are here, and a function which may cut like this, right? So here it cutting horizontally, one horizontal line, that means f dash of a and f dash of b is going to be equal. But as you can see here, there are many points which is where f dash, the derivative is going to be 0. So that's why it's not a unique one. Similarly, as you can see in the two pictures, as you can see here, this is also going to be a point where f dash of c is going to be 0, where now the statement says that let f be a real valued function continuous on a closed interval. So if we have defined a b to r as a continuous function and fx is differentiable in an open interval, f dash exists for open interval ab, and f of a and f of b is equal to, so f of b are equal, then there exists c belongs to ab such that f dash of c is going to be 0. That is our statement. In other words, if 2 points of the same height are connected by a continuous differentiable function, then there has to be at least one place between those 2 points where the derivative or slope is going to be 0. As I have said you that if it has the same height, right, so there must be some point, at least one point where derivative or slope is going to be 0. So that means we have a parallel horizontal line at least at one point, tangent line, right? So since the function is continuous on a closed interval ab, it is bounded, and in that sense its bounds. So let m and capital M be its infimum and supremum, right? So m is the greatest lower bound and supremum, that means it is the least upper bound respectively of the function. Then there exists a point c and d of ab such that fc equal to m and fd equal to capital M, right? So there are two possibilities, either m equal to m or either m is not equal to m. Now we can explore the two cases as well. So first case we consider m equal to capital M, then f is a constant over ab, right, as it is given here. So therefore its derivative is going to be 0. We had already done that, right? So any constant function had derivative equal to 0 for every x belongs to a and b. And when m is not equal to m, both of these cannot be equal to the same quantity fa. At least one of these, say m, is different from fa and fb. so that fc equal to m and that is not equal to fa, right? So that means c does not equal to a. Fc is equal to m, that does not equal to bfb. That means c does not belongs to c is not equal to b. So we had proved that the point c is not going to be the end points if we take infimum and supremum unequal. And if we take supremum and infimum equal, that means the function must be constant. Otherwise, supremum and infimum is quite different. The maximum lower upper bound and the greatest lower bound must be different, right? So that's why in the case where we had m equal to m, f dash is going to be 0 everywhere because the function become a constant function and the derivative is going to be 0. But if m is not equal to m, then c is not going to be the end point. So infimum is not going to lie and at the end points. This means that c lies in an open interval ab, right? So we shall now show that c is the point where f dash of c is going to be 0. So if f dash of c is less than 0, use the statement or use the procedure where we had proved Darbox theorem. So using the same manner of the approach, so that means f dash of c is less than 0, that means fx is less than fc for each c plus delta 1, right? And if f dash is greater than 0, then fx is less than fc for each point of c minus delta 2 to c, right? And which is a contradiction. So there is no, I mean, it cannot happen like this because it contradicts the definition of infimum, and hence for f dash of c is equal to 0. So this statement here, this approach is the same as the Darbox approach, right? As you can go through it, this is the same approach as the Darbox theorem. So that was the proof. Now look at a different theorem. We call it extreme value theorem. If a function fx is continuous on a closed interval ab, then on a closed interval ab, right? Then fc attains both a maximum value capital M and a minimum value small m in the interval closed interval ab. These maxima and minima can occur at interior point where f dash of x is 0, at an interior point where f dash of x does not exist, or at an end point of the interval. So extreme value theorem, if a function fx is continuous in a closed interval ab, it is a typo here, then fx attains both a maximum value m and a minimum value m in the interval ab. These maxima and minima can occur in interior point of ab such that f dash of x is going to be 0, at an interior point where f dash of x does not exist, or at an end points of the interval. So there are three things which it says that the capital M and small m, which are the maxima and minima of a function, it's only occur where an interior points, and if it occurs at interior point c, then f dash of c is going to be 0, right? An interior point where f dash of x does not exist. It is also possible where c belongs to ab, but f dash of c does not occur, do not exist, right? Or at an end point of the interval. So it might be c equal to a on right of b, right? So that is what the extreme value theorem says, that maxima and minima of a function in a closed interval, if the function is continuous in a closed interval ab, then maxima or minima may exist an interior point. If it exists an interior point, then the derivative f dash of x at that point is going to be 0. It may be possible that it exists an interior point and f dash of x does not exist, or sometime maxima or minima may be at the end points itself. So there are three possibilities for maxima and minima of a function. So using this extreme value theorem, we can prove the Rawls theorem in a different way. So let me state the first one. So assume that function f is continuous on the closed interval ab and differentiable on the open interval ab, and fa equal to fb. So end points have the same value and the function are continuous and differentiable in a closed interval and open interval respectively, then there is at least one point C between A and B, so that f dash of C is going to be 0. That is our theorem, and we are going to prove using the extreme value theorem. So, since fx is continuous on a closed interval AB, f has a maximum value capital M and a minimum value small m. This follows from the extreme value theorem, as we had already seen here, right? We had already seen this one, right? Extreme value theorem, where fx is continuous on a closed interval, then the fx attains maxima and minima in a interval AB. So, case 1, if both maxima and minima is equal to, then fx is going to be some constant function, and once it is a constant, f dash of C is going to be 0. So, f dash of x equal to 0 for all values of x in AB. It follows that f dash of C is equal to 0 for some value of C, right? Case 2, if M is less than capital M, then both M and M cannot occur at end points AB. Since FA equal to FB, thus at least one occurs in the interior of the interval x equal to C. So, it follows from theorem B and C that f dash of C is going to be 0. So, what will be the geometrical interpretation of the Rawls theorem? In general, we took end points equal, and once we have end points equal, then we believe that there must exist some point where the slope is going to be 0. The tangent line is going to be parallel to the horizontal axis or some horizontal line of that point, right? So, as you can see here, these are the curve of, this is the curve of the function fx. So, this is the fx, and this is a closed interval AB. So, here we have at the value are the same. So, value at both point FA is equal to FB here. So, we can use the Rawls theorem, and there must exist some point in AB such that f dash of C is going to be 0, the slope is going to be 0. This point, look at this point has the slope is going to be the 0, because this horizontal line, the slope tangent line is parallel to the axis or this line as well, right? So, that is what the geometrical interpretation of the Rawls theorem is. Let me give you some examples, and then we will validate the Rawls theorem by taking this function. So, check the validity of Rawls theorem for the function fx equal to x square minus 6x plus 8. So, this is the function. As you can see, this function is a continuous function and as well as derivable function. So, we can have the differentiability at f dash of x is equal to twice of x minus of 6, right? So, that means the Rawls theorem will be applicable, and let me check for the interval. So, f of 2, I can find f of 2 is equal to how much? 4 minus of 12 plus of 8 is equal to 0, and f of 4 is equal to how much? 16 minus of 24 plus of 8 is equal to 0. That means f of 2 and f of 4 are equal, and the value is going to be 0. So, we have a horizontal line at the end points f2 and 4. So, we expect there must some of the points where the slope is going to be 0 or the tangent line is going to be parallel to the horizontal line or horizontal axis, right? So, by Rawls theorem, there exists a C belongs to 2, 4, where derivative f of f dash of C is going to be 0. That's we are expecting. So, let dash f dash of x is calculated here. This is equal to 0. So, x is equal to how much? 6 by 2 equal to 3. Now, 3 lying between C is nothing but C equal to 3. So, C lying between 2 and 4. So, that is the validation of the Rawls theorem for this function. Let fx equal to x square plus 8x plus 14, find all values of C in the interval minus 6 minus 2 such that f dash C is equal to 0. So, now we have to prove about minus 6 and minus 2. that there must exist C some point in that interval, the derivative of that point is going to be 0, right? Since function is given, so I have to firstly check the value at the end point. So let me check f of minus 6 and f of minus 2. So f of minus 6 means 36 minus of 48. So 36 minus of 48 plus of 14, and this will be equal to 46, right? So 10, 50 minus 48 is equal to 50 minus 48 is equal to 2. Similarly, f minus 2 is equal to 4 minus of 16 plus of 14 is equal to 18 minus 16 is equal to 2. So now as you can see here, the function has the same value at minus 6 and minus 2, right? So between these 2 points, we must have some point C for which the function has the tangent line parallel to the axis, or the slope of the curve is going to be 0, right? So now use this theorem and find out firstly f dash of x. So what will be the f dash of x? F dash of x is equal to twice x plus of 8, and this is going to be 0. So x equal to minus of 8 by 4 equal to minus of 8 by 2 equal to minus of 4, right? So this minus 6 and minus 2, there is a number C minus 4 for which f dash of minus 4 is equal to 0. So the C point we have already calculated as C equal to minus 4, and this will validate the Rolle's theorem. Example 3, given the function fx equal to x square minus 6x plus 5, find all values of C in the open interval 2, 4 such that f dash of C equal to 0. Now function is given and there will be asked that find the point in a given open interval 2, 4 such that its derivative of the function at that point is equal to 0. That means they are indicating to use the Rolle's theorem, right? And how we can use that one? Firstly, I have to find out the value of the function at those two endpoints. So we are going to find out f of 2 and f of 4 first, and then we will look for the equality. That means f of 2 must be equal to f of 4. If it happens, then we will going to find out the point C in 2 and 4 such that f dash of C is going to be 0. That will be our approach. So let me do this. So for the endpoints, f of 2 is equal to how much? 4 minus of 12 plus of 5 is equal to 9 minus of 12 is equal to minus 3, right? And f of 4 is equal to 16 minus of 24 plus of 5. So this is 21 minus of 24 is equal to minus 3. So here f of 2 is equal to f of 4. So we have some of the function like this, where we may have these 2 points 2 to 4 such that their values are equal. Now we have to find out some of the C point, some C points here. Maybe there are different C points, but C points such that f dash of C is going to be 0. To find out C, firstly we have to calculate f dash of x. So f dash of x equal to how much? 2x, this is equal to 2x minus 6, and this is going to be 0. So x equal to 6 by 2 equal to 3. So that means there is a point 3. This is the point 3. We have to find out f dash of 3. So f dash of 3 is equal to how much? 2x minus of 6 equal to 2 cross 3 minus 6 equal to 0. So by the Rolle's theorem, it is true that 3 will be the point C. So the value of C equal to 3 such that f dash of C equal to 0. So we have find out 3 minus 3 minus 3, f dash of C equal to 3. As it is always says that f is a continuous function, f is a continuous function in a closed interval AB, and then we have the function is derivable in an open interval AB, and the end values are equal, then we will have a point C between A and B such that f dash of C equal to 0. If f dash of C equal to 0 for A and C and B, then can the function be continuous or can the function be differentiable? That is what we are going to give you by the counter example. Consider fx equal to modulus of x. Obviously, modulus of x, we all know that it is a continuous function everywhere, but it is not differentiable at 0. Modulus of x is not differentiable at x equal to 0, right? So, firstly find out what will be the value at the function modulus of x at minus 1, that is 1, and what will be the value at modulus x at minus at 1 is equal to 1. So, there is no point inside the interval at which the derivative is equal to 0, right? Even though the function is continuous in a closed interval, the Rolle's theorem fails here because fx is not differentiable over the whole interval. So, now you can imagine why the Rolle's theorem, the statement contains fx is maximum in a closed interval as well as fx is differentiable in an open interval AB, because some of the examples where the Rolle's theorem fails, not valid. Similar example are here. The linear function fx equal to x is continuous on a closed interval 0, 1 and differentiable on the open interval 0, 1. The derivative of the function is everywhere equal to 1 on the interval. So, the Rolle's theorem fails here. This is explained by the fact that the third condition is not satisfied. That means f0 is not equal to f1, right? So, any of those three conditions if not satisfied, then the Rolle's theorem is not valid. Similarly, consider a fractional part of the function fx equal to fractional of x on the closed interval AB. The derivative of the function on the open interval 0, 1 is everywhere equal to 1, right? In this case, Rolle's theorem fails because the fx has a discontinuity at x equal to 1. Everywhere we had discontinuity, that is, it is not continuous everywhere on the closed interval 0, 1. So, you can look at this value 0 and 0 here and 1 here, right? And what will be the fractional part of this? So, this is the fractional part here, but what will be the value of 0 and 1? So, that will not valid here, right? So, that is why it is not a continuous in a closed interval AB. And let me remind you these three conditions for a Rolle's theorem. So, Rolle's theorem only valid when these three act together or valid simultaneously together. If one of them, any one of them is not present there or not there, then this Rolle's theorem is not applicable. So, that is all for the Rolle's theorem and their applications, and I think you do understand that if we use the Rolle's theorem, we can find out an interior point between these two endpoints, so that f dash the derivative at that point is going to be 0. So, that is all. Thank you so much.